All right, now we'll take a look at parametric functions and how we can relate these to derivatives that we've already seen. So first of all, if you haven't already, you should take a look at 1.4 parametric equations, where we take a look at graphing parametric equations and just making sure we remember, what those are. All right, so if we have some set of parametric equations, x equals f of t, y equals g of t, this crazy looking curve over to the right here, that's x equals t plus sine of 2t, y equals t plus 2 cosine of 5t. And you can see that parametric equations can allow us to graph some things that we would never be able to graph using just our standard Cartesian equations. All right, so if both the functions f and g have derivatives at some value of t, then the curve has a derivative at t, and that derivative would give us the slope of that curve at that point, x of t, y of t. So let's take a further look into this. So if we want to find the slope of a curve at any value of t, we find dy dx. Well, dy dx would be dy dt over dx dt. And if you think of canceling the t's, that gives us dy dx. So the units here, all that kind of makes sense. And we have to assume that the denominator is not equal to 0. Okay, now we need to find the second derivative, which would give us concavity. In order to find the second derivative, we find the derivative of the first derivative. So that's the second derivative of y with respect to x would be the derivative with respect to x of y prime. But keep in mind that y prime is a function of t. So to take that derivative, it's the derivative of y prime with respect to t over the derivative of x with respect to t. All right, so we want to find the second derivative of these parametric equations right here. So we start by finding dy dx. dy dx is dy dt over dx dt. So find dy dt, find dx dt, and there's our first derivative, dy dx. So finding the first derivative is not too complicated. Take the derivative of y over the derivative of x, and that's it. Finding the second derivative usually ends up being a little bit more complicated, and let's take a look at how things end up there. So we want to find that second derivative, which, recall, is the derivative of y prime with respect to t over dx dt. So y prime is what we have right up above there, 1 minus 3t squared over 1 minus 2t. So if we take that derivative with respect to t, we need to use quotient rule. And then dx dt is just the derivative of x, which is t minus t squared. So if we take the derivative of y prime, we use quotient rule, low d high minus high d low over the square of what's below, and the derivative of t minus t squared is 1 minus 2t. We have this fraction over a fraction. Well, let's simplify that down, and that ends up giving us 1 minus 2t cubed in the denominator. And if we collect like terms, we end up with a simplified form for the second derivative right here. So not too bad, but we just have to remember that the second derivative of y with respect to x is the derivative of y prime with respect to t over the derivative of x with respect to t. All right, if we want to analyze parametric equations or parametric functions, we need to know a few things. So we've already seen that the slope at any point, that's dy dx. The concavity at any point is the second derivative of y with respect to x. If we want to find a horizontal tangent, if you just kind of think through this, horizontal movement is going left to right. And so if we stop and change direction while moving to the right or moving to the left, that would be when dx dt equals 0, because the movement in the x direction has stopped. And if we want to find a vertical tangent, that's when we change direction going up or down, so dy dt would be 0. And along that same thinking, if we wanted to find the highest or lowest point, that would occur when dy dt equals 0. And to find the leftmost or the rightmost point, that would occur when we let dx dt equal 0. All right, so let's take a look at an example here. We want to graph this curve, and we'll use our calculator for this. So go to the parametric graphing on your calculator and plug these in. T goes from 0 to 3.14, and we get this curve. And notice your calculator over there at the right doesn't show the last little bit of the curve. It actually does exist there until we get all the way down to the x-axis, but the calculator just kind of has trouble there at that endpoint. Okay, we want to find the highest point on the curve. So the highest point, that's when we change direction going up and down, which would be when dy dt equals 0. So let's find dy dt, and let's set it equal to 0. So we get 2 cosine of t equals 0, and over our interval from 0 to pi, cosine of t equals 0 when t equals pi over 2. So we know that the highest point is going to occur when t equals pi over 2. If we want to find what that point is, let's plug that into the original parametric equations. So x equals pi over 2 squared minus 5, y equals 2 sine of pi over 2. And let's just get that in decimal form right there. X is negative 2.533, y is 2, which gives us that point right there. And we can see, graphically that makes sense. Next, let's find the slope at the point negative 5, 0. Well, when x is negative 5 and y is 0, t equals 0. And if we look up at our parametric equations, we can make sense of that, because if x equals negative 5, well, then t must equal 0. And if we plug in t equals 0 for 2 sine of t, we also get 0, so everything works out. So identifying the slope at the point negative 5, 0 is the same thing as saying identify the slope when t equals 0. So we find the slope, dy dx. dy dt is 2 cosine of t. dx dt is 2t, evaluated when t equals 0, and we end up with 2 over 0, which is undefined. And that makes sense when you look up at that graph. As we get closer and closer to 5, that slope just keeps getting steeper and steeper. So at that point, negative 5, the slope is undefined. The final equation we need here is the length of a parametrized curve. And the equation is similar to our length of curve equation we've already seen. And here it is. The length is the integral from a to b, and those are values of t, of the square root of dx dt squared plus dy dt squared. And notice this appears to be like the Pythagorean theorem, which is one way we can show how to derive this. That'll help you kind of remember what this equation is.